All right, so today I'm going to talk about the project that the BirdCLEF 2023 team, as part of data science at Georgia Tech, worked on. So this last semester in the spring, we worked on transfer learning with semi-supervised data set annotation for bird call classification. And this is a team of 4 of us, although there were many people kind of spread out throughout the semester trying to figure out whether this was the right fit for them. So this competition team is the second iteration of the Kaggle competition teams that have been running here at Data Science at Georgia Tech. I've kind of led all the efforts there, and this group that is here is kind of an evolution of that, hoping to get more people doing the same thing that I've been doing. So in the spring, or actually in the winter of last year, I recruited a team to do this competition. We ended up having a team of 3 master's students, all in the OMSCS program, and 1 undergraduate student. He's a 2nd-year computer science student. So we had a nice team to kind of go through this project. The technical approach to this was to, we're solving this bird call classification problem where we have lots and lots of audio from bird calls. So we use a sound separation model to separate sources and denoise. We use a off-the-shelf deep learn or a convolutional deep neural network to embed audio to create discrete time series. We do some pseudo labeling to solve for some of the really challenging problems in just the representation of the problem. And we do some just basic supervised classification. And all these techniques together gives us a pretty okay solution to the problem. So this is the team. There's myself. There is Nathan, who's the undergraduate who joined us. There's Murilo. He joined the team when I presented about BirdCLEF at the OMSCS conference in the spring. And then Chris, who was with the team since the beginning, also OMSCS. Yeah, that was the team. And we worked on the BirdCLEF problem. Like I said, it's classifying a bunch of audio to figure out where in these hours and hours and hours of audio, where there's a bird call and what species that bird call is. And this is useful because you can have a bunch of these autonomous recording units out in the wild. Maybe researchers go out and they identify areas that might be really good for seeing the population of birds and just identifying what birds there are. It's challenging in a couple of ways. One is because audio is really dense. It's represented as 32,000 samples per second, and you have, each of those samples might be a floating point number, and so you have to be able to process this data in a way that makes it easy for you to do that classification problem. So there's a bunch of audio that we get from Xenocanto, which is a crowdsourced database of bird calls. And the thing with this is that the data is not really labeled. You get an audio clip and it has a species of a certain kind, but you don't know what time labels had that actual bird call. So there's this labeling problem that's fairly challenging to get. So we have audio's dense, hard to represent in traditional supervised learning contexts, and we don't have hard labels that we can use to train a supervised classifier. So we went in and we read the literature. There's these 2 interesting models. The first is a domain-specific deep learning model called BirdNet. BirdNet does this classification of audio by chunking audio into 3-second clips, doing a spectrogram, taking the transformer that over time to get a spectrogram, and then doing image classification on the spectrogram. And the idea is that we want to reuse this component in a way that will classify a new set of bird species, which is kind of challenging. The second part is this model called Mixit, in particular BirdMixit. This is a sound separation model, so it's able to listen to a piece of audio and then split it up into 4 or 8 tracks, depending on the model that you use. But this is solving what you might have heard of, like the cocktail problem, where you have multiple people speaking in a room and you want to be able to disambiguate between them. So the idea is that we can use a sound separation model to denoise the problem and maybe get the track that has the bird call that we want. So our approach, as I said before, is to use the sound separation model to separate the audio. Then we have BirdNet to generate embeddings and labels, generate pseudo labels, and we do the classification problem. So Mixit is actually pretty simple. We just run it through their model. And in the top, you'll see the original audio clip. There's 3 main visible sources in here. You can see that very top call at 8K. And then there's another smaller call that's kind of hard to see, but it's roughly between 2 and 4K. And then there's like the very visible bird call between 1 and 2K. So you can see that the separation model will separate it, and we see in source 0, in source 1, and in source 3 how this audio gets separated out. And then once we have that, we can pass it through the BirdNet model. An embedding is a space where data points in your original space they get mapped into an embedding space which has fewer dimensions, and in this embedding space all of the points are the same distance as they were in that original space. So you can use this as a way to reduce the dimensionality but preserve this idea that things that are similar and things that are distant. And you can see that when we pass the audio through the embedding model and we project it down to 2 dimensions, there's a very clear clustering behavior going on. So on the left is against all the data, on the right is against the top 7 species. And you can imagine building a supervised classification model that is able to almost like completely separate these into their individual classes. So this idea of just taking the audio, embedding it, and then clustering it or doing some sort of classification is justified by this kind of like squinting at it a little bit and seeing this clustering behavior. BirdNet also gives us these soft labels. So it already has, I think it's 3,000 or 4,000 species that it's been trained on. So we can run all the audio through it, and it'll give us, I think it's this species with this confidence. And we can take that data and we can use it to generate new labels for our classification problem. And what we want to do is we want to be able to use BirdNet to generate concrete labels. So we'll take the audio, we'll embed it. Now we have a time series that's discrete. And for each of those time steps, we want to label it whether it has a bird call or not. So BirdNet will give us, I think there's a bird call in here. I think it's this species. But instead of using that species that it spits out, we use the label that's given to us based on which species category it's part of. So here you can see a Beth R1. I'm actually not sure what bird species that is, but like we would associate that call with that species. So it's like a pseudo labeling process. And the final part is just running it through a classification model. So here we've just done a call no call model. So given a piece of audio, is there a bird in it or is there not? And we can see with the top 3 models, we actually do get pretty good performance on disambiguating between background and foreground, or like a bird call. So now we want to be able to do this with the full set of audio clips that we get from the competition. So while going through this, there were quite a few engineering problems. The 3 that I have identified to just talk about are the pre-processing of the audio data, the time resolution mismatches, and the classification implementations and why we chose them. So the first is pre-processing the audio data. we want to pass all the audio that we have. I want to say it's 900 hours. It's a lot of audio that we need to listen to. And so what we need to do is we need to pass it through the sound separation model, and then we need to pass all of the sound separated audio through the embedding model. And so how we do this is we set up a data pipeline using Luigi. Luigi is a tool that sets up directed acyclic graphs of tasks to be run. So we can run this on a computer, we can leave it on for several days, and it will take advantage of the full capacity of the computer. So if there's 16 cores, then I'll use all 16 cores to schedule work against. So we're maximizing our use of the computer to run all the data through. We take each audio clip, we truncate, we split it up so that it's short to avoid data skew. Then we pass it through the sound separation model and the BirdNet model, and we generate this one big Parquet file where we can just treat it as this one data set. This was a fairly challenging piece of the work, and it took several weeks to implement in a way that we felt useful. But this is kind of an important process because it's hard to do anything else without having this nice, clean data set to work against. Then after that, we have these time resolution mismatches. So the BirdNet model wants to spit out embeddings that take 3-second audio clips. But when we submit to the competition, they want to know at every 5-second interval, is there a bird call or not, and what species is it? So we have to resolve this idea of there's these 3-second audio, like we have a 3-second sliding window that we can transform the data in. And we have this 5-second non-overlapping window where we want to be able to spit out results for. And we took quite a few different approaches to this. But the idea is that we either concatenate or we average embeddings for each of these time windows. And we can kind of get around that. The final piece here in engineering problems is classification performance. And I say performance in the terms of like implementation performance in terms of CPU time. So we ended up finding that our best model is actually a really simple linear model, a logistic regression model. But when we try to fit that data against the model, it takes 60 minutes to build that model. And so when we're trying to iterate against a bunch of these different augmented data sets, the time that it takes to fit these models is pretty important. So we found that logistic regression worked fine, but it took an hour. We tried SVMs. They took a little longer, but comparable performance. We tried MLPs or neural networks. They take way too long in terms of like hyperparameter optimization, so out the window. And then we used XGBoost using a GPU implementation that does histogram binning on GPU, and it runs pretty quickly in 5 minutes. So we have all these models, and we decided to go with XGBoost because its implementation was fast. It got us results that were comparable to the logistic regression model, and that's how we went about that. We tried a lot of different things, and we found one that met our constraints for this problem. So onto the results. I'll talk about overall performance, and then I'll talk about some of the experiments that we did. So overall performance, we found that after we embed things, and then after we generate these pseudo labels, when we run that classification problem with logistic regression, we get a public score that is better than the baseline notebook that the Kaggle competition presents. And that Kaggle notebook uses a very recent Google deep learning model for bird call classifications. It has 10,000 species, and all those species are represented in this competition. So when they ran their model, they got some score. I believe it was 0.72. And so you can see that our model that used use BirdNet, and a very simple logistic regression model was able to transfer that performance more so than that other model that Kaggle provided. So we did better than the very baseline of the competition, which is a big plus. But we found out over time that it was kind of hard to get better than that. So there were a couple of experiments that we ran. The first is like, how do we generate the best pseudo labels for the problem? And we found that the best way to do that, well, we tried a couple different ways, and it's hard to say what the best is. But we used the primary class of the track as the label, and we used the confidence of the BirdNet model to determine whether it's a call or not, whether to label it on or off for that species. And then we also tried variations of that. So we had multi-label classification, where we would have multiple labels per time segment. So you might have the primary class, and then you might have a secondary class that's associated with the BirdNet model. And we tried both of these. It's hard to beat the just very simple model. In terms of data augmentation, we had some ideas about how to improve just the baseline single embedding for the class. One idea is that, so this very first equation is just, we're training a model on the current timestamp that's generated by BirdNet, and we're spitting out a result. Another idea is that maybe we can use the current time step and the next time step to see whether we can make a better prediction. The third one is using the current time step and the sum of all the embeddings in the track. So like this kind of global embedding plus the current time step to determine whether it's going to be one species or not. And then the final one there is using the current time step concatenated with the next time step concatenated with this global average embedding. And we found that none of these really improved the model all that much. There were kind of implementation details and maybe more rigorous ways of experimenting with this, but these are some of the approaches that we took while we were experimenting with the models. So I got this big slide, not split out into pieces, but if you're going to do this again, I think there are 4 big points. The first is that I think we should have tried a more rigorous approach to evaluating the semi-supervision part of the problem. So we never really built that baseline against the problem where we didn't include the mix-it model. So we always included the sound separation model in our in experiments, but we should have done some sort of ablation study to see whether that contributed or not to the problem. The second is it'd be interesting to try different embedding models. So we use this domain-specific bird call classification model to generate the embedding layers, but there's all these other models that are meant for audio or human speech that would be kind of interesting to see if you could get some sort of clustering behavior between bird species. So there's this model by Meta called AudioGen, which is a general purpose diffusion model, I believe, or at least a transformer model where you just feed a bunch of audio in it and it does this sequence model to predict what the next time step is going to be. So using that as an embedding layer could be cool. OpenAI has this Whisper model, which is similar. It's meant for human speech, and Mozilla Deep Speech is also another speech model. But it would be interesting to try different embedding models and to use the same approach that we did in this competition to see whether those have an effect on the performance of the supervised classification model. The third is it'd be interesting to look at the embedding dynamics. So by dynamics, we're taking a look at a series of embeddings over time, and we want to be able to see how that changes over time. So you can learn linear dynamics of a time series through some pretty clever representation and doing, through clever representation. I mean, you can find this idea of like a forcing function where there's a there's this function that goes up and it causes the dynamics to swap in audio. And so I think you could combine this with motif mining to figure out whether there's going to be a bird call in a piece of audio just based on the dynamics of the embedding in a certain window of time. And I think that would be an interesting direction to go. The final is the trying out sequence models. So a sequence model is you have a bunch of embeddings time after time, and you just want to learn what the next sequence is going to be. So all these large language models are sequence models. You take a bunch of tokens and you try to predict the next token. And it would be interesting to do that in the context of bird calls. And I think it could be pretty efficient and it could be end-to-end because all of that can be done on a GPU directly. So that is all for kind of the technical pieces of the presentation. I have a couple more slides. Just talking about like being part of Kaggle teams and leading something like this yourself. I presented some of these slides at the OMSCS conference, and I thought it would make sense here. Although, this applies to more than just online master students. This is for everyone who is here in the club, on campus, off campus, undergrad, grad. So if I were going to give myself advice 2 years ago, when I was starting, I found out about data science at Georgia Tech. I would initially say go and build that team. The very first time I did the BirdCLEF competition, I did it on my own, and I did some interesting things, and then at a certain point, it's like this is as far as I'll go, and I stopped. So having a team will help you push you over that finish line. So you should build a team if you're going to compete, because there's a social aspect to a team, and there's expectations when you join one, that you'll do something, you'll accomplish something, you'll have something to show for all the effort that you've put into a group thing. The second is you should be prepared to lead a team. And leading a team requires organization. It requires communication. And you kind of need these where you're closely collaborating and trying to achieve a goal. And secondly is that everyone on a team is capable of contributing. Like everyone here is at Georgia Tech, and people at Georgia Tech are pretty smart. So it's good to acknowledge that everyone has their own schedules and everyone is capable of contributing. So it's good to recognize those contributions. And then this last piece is for the OMSCS folks. But for, it's good to know that people who are doing these online master's programs are generally working professionals, and working professionals usually have a couple of years of experience under their belt, like whether it's using, writing code for something, working on a large code base, having some idea of version control, some understanding of how systems get put together, using particular tools like Spark or Pandas or something. These professionals have a lot to bring to the table. And I think it's worth reaching out to OMSCS and OMSA when you're building out these teams. Outreach is important. I use the Data Science Club to kind of outreach and find teammates for this. And the OMSCS program has this nice forum for all the students. So there's a couple thousand students at any given time in the program. And so by posting it on the forum, you'll get a lot of eyes. And there have been a lot of people in this particular group. So I can vouch for its efficacy. And finally, just be on the lookout for opportunities. This is one of the reasons why I put together this group. It's because it's kind of hard to find opportunities when you don't know that they're there. And I think by introducing everyone to Kaggle, forcing people to kind of take a look at competitions and to build notebooks, kind of brings it to the front of mind, and just kind of showing people that CLEF exists and that they accept working notes makes it a little easier to get your foot in the door. So thanks to everyone who's been involved in the last couple of years. These are kind of like the big iterations of the team. 2022, this fall 22 EDA like group, and the 2023 group, alongside the leadership for helping me make the project a thing. There's a couple of resources in here that are interesting to look at, mostly the proposals and whatnot, and the original working notes for the 2022 competition. Yeah, with that, I am done, and I will also stop the recording. Let's see, stop share, and